Hello physics students, this is Mr. Dillick. This is physics video number 3, and it's about how we go about graphing motion. Now that we've talked a little bit about some of the basic things that you need to understand about motion, frames of reference, and quantitative versus qualitative physics, really what I want to do is I want to remind you that when you're answering a question in physics class or on a physics test, really there's, I think, 3 different ways that you could successfully explain that you understand the physics of a situation. One of them, and probably the most popular way, is using math. That's when you come up with an equation and you arrive at a mathematical relationship that can be quantified. And what makes this one, I think, my favorite and most physics teachers' favorites is because it's universal. Math is universal. It means we could probably show that physics equation to people in different countries and they would understand the physics of what we were trying to explain, because math is a pretty universal language. It's also the easiest, least time consuming for you to put together, and least time consuming for me to understand, to quickly look at and see if you understand the physics of a situation. So one way we can answer a physics question is with math. The second way is with a graph, and we're going to spend a lot of time talking about graphing today. By drawing a graph, you are illustrating the relationship between the variables visually, which means you're still telling me about the physics of the situation. You're explaining to me in the same way an equation would, whether these variables are directly related or indirectly related or not related at all. It's just a different way of doing it, and for some people who are kind of visual, verbal people, a graph is actually better than math and easier than math. And then there's a narrative. This is the most time-consuming way to describe what's happening to the physics of a situation. It's also the hardest to explain, and for someone grading that to really interpret whether or not you get it or not. It has the least amount of objectivity and the most amount of subjectivity. So that means it's the least preferred method. But really, all of these are equal in value, and the best way to answer a physics question would be to do all 3. But what I like about graphing is that we can easily take a graph and turn it into math. It's easy to get the math from a graph, but it's just as easy to take a graph and turn it into words. So it kind of bridges the gap between math and some narrative way of explaining it. Most students struggle with graphing, and I spend a lot of time talking about graphing because it's just something you don't get a lot of skill in. In math class, you get some practice doing the equations. In English class, you get some practice explaining things and verbalizing things in words. But only in science class you really do a lot of graphing, where you're trying to integrate those 2 worlds. So we're going to spend some time on that today. There's really 3 types of graph that are pretty common in physics, especially early on: the position time graph, the velocity time graph, and the acceleration time graph. PT graphs, which is another name for position time graphs, usually have specific names. Maybe XT if the object's moving left and right on a number line, YT if it's moving up and down, for instance. And the position time graph is the most basic, simple, and most important of the graphs that we would be interested in. You can answer a lot of questions with a position time graph, and I've gone out of my way to indicate some of the questions I might ask you on a test. From a position time graph, you can answer the question about where the object is located relative to the point of reference, whether or not it's moving relative to another object, where did it start, where did it end, how fast was it moving at a specific time, did it ever change speed, is it speeding up or slowing down if it is changing speed, where was it located when it started to change speed or when it actually did change speed. What direction is the object moving at a particular moment in time? Does it ever change directions? How many times does that happen? Where is it located when it does change direction? And on and on and on. So you can see there's a lot of questions we could ask. And I want you to be pretty good at answering those about a position time graph in particular. The velocity time graphs and acceleration time graphs, you're going to see less frequently, but you still need to know them. So when we talk about a position time graph, there's 7 key things that you should look for. The first thing that you should really look for is what the label on the graph is. The fact that this is an XT graph means that we have an object that's moving left and right, and we're measuring that in meters and seconds. A lot of people skip that step, and then everything else they interpret about the graph from that point on is wrong. then from there, we really want to recognize what the point of reference is and what it means. And the point of reference is always located right where those two axes come together. It's literally 0 on this number line and 0 on this number line, and represents a physical object that we're using to look and see that an object is moving. So if a car passes a intersection on a road, that intersection could be a point of reference that helps us see that the car is in fact moving. Most important thing that I want you to know about the point of reference really has to do with position, and that is, you have to keep in mind that if this is 0 on the number line, everything above that is positive, everything below that is negative. Everything to the right of that is positive, everything to the left of that is negative. And so this origin really gives us a point of reference that we can say, was the object regularly located to the right in this positive direction, or was it located to the left of the point of reference of that object that we're interested in? And so if this line spends most of its time down here, then it's located to the left. And if it's over here, then in the first quadrant, then it's going to be located to the right of that point of reference. Now don't get that confused with the direction it's moving. Something could be located to the right but moving to the left, or located to the left and moving to the right. And so don't confuse which way it's moving with where it's located. Then there's the origin. The origin is really going to be our y-intercept. Now I know this is labeled x, but this is the y-axis and this is the x-axis, like you would do in math class. And so wherever the y-intercept is, that's our origin. We're also going to be interested in our endpoint a little bit. Let me show you what I mean. Okay, so I've added some lines here, and when we look at this, I'm trying to make this qualitative. I'm trying to get you to avoid thinking about the numbers. And instead, what I really want you to think about is what we can learn from this graph based on what we've talked so far. So we know it's moving left or right. We know that it's doing that over time. We know that this point right here is some object that we're interested in, that it's nearby. And up here in the positive direction, remember, positive x means to the right and negative x means to the left. So that means both these objects have an origin, an intercept, that's in the positive direction. So imagine this was positive 1, and here's positive 2, and here's positive 3. What we're saying is that it's located initially to the right of the point of reference. Now the red one kind of keeps getting further to the right, right? As time goes on this way, this line gets more and more positive. But the green one, as time goes this way, gets kind of less and less positive, becomes 0, and then becomes more and more negative. So what does that mean? Well, this is the origin, but here you can see this is the end point. The end point, and it doesn't necessarily mean when the object stopped moving, it's just when we stopped paying attention. Here we can say that the end point is further to the right than the actual starting point. So its origin and end point are the third thing that I'm really interested in. You can see the green one started to the right, further to the right than the actual red one did, but ended up way to the left of the point of reference. Okay, so the next thing we want to look at is whether we're looking at lines or curves. And on position time graphs, lines and curves mean different things. These are both lines, or they're pretty much lines. If they were curves, it would mean something really different, and here's why. These next three things we're going to talk about, slope, direction, slope, magnitude, and lines or curves, really have to do with the key most important thing about understanding graphing, and that is when you look at a graph and you see it's a position time graph, you must remember that the slope of a position time graph tells you the velocity of the object. We mentioned that in a previous video. So what I mean by that is a velocity has both a magnitude and a direction. So we're interested in the magnitude of the slope and the direction of the slope, and whether or not it's a line or a curve, because lines have constant slopes, but curves have changing slopes. So the fact that these are lines tell us that the velocity is constant. It tells us that this isn't an object that's accelerating. This is an object that's moving at a constant speed. Now, this one happens to be sloping in the positive direction. That is, that its rise over its run is a positive number, whereas this one happens to be sloping in the negative direction. That is, its rise over its run is a negative number because the run is downward on this axis, so it's a negative run. And so what we see is that this represents something moving in the positive direction, which is to the right, and this represents something that's moving in the negative direction, which means to the left. Now, if we looked at them and we could figure out which one had the greater magnitude of its slope, that would be the one that's moving the faster. So, whether the fact that it's a line means that it has a constant slope, and the slope is the velocity, so it has a constant velocity. Both of them do. One of them is sloped positively, which is the positive direction is to the right. One of them is sloped negatively. The negative direction means to the left. So this one's moving to the right. This one's moving to the left. And it's kind of hard for me to tell, but they seem to have pretty equal slopes. So what's happening at this point? Well, that's where they actually are occupying the same position at the same time. So they basically are passing each other, or maybe even running into each other there. But what we can see is that this one starts to the right, ends up to the left, because it's always moving to the left. So it actually starts to the right of the point of reference, passes whatever the red thing is, passes the point of reference, and then ends up far to the left. And it moves at a constant velocity that whole time. Whereas the other one starts a little bit to the right, not as far to the right as the green one did. They pass each other here. This is the point where they pass. Never comes back to the point of reference, keeps moving at a constant velocity further and further and further away to the right until it eventually ends far to the right. What about velocity time graphs? These are considerably trickier, so I'm not going to ask as many questions about them, but you do need to be pretty familiar with them. The 7 things that you're looking for are the same 7 things. Make sure you pay attention to the axis. This one happens to be something with a velocity x, so it's moving right and left. If that was a y or a z, it would mean something different. And we see here that it's measured in meters per second, and we're comparing it to how that velocity is changing with time. And so in this case, the slope of a velocity time graph tells you acceleration. Now, what you need to know about accelerations is they go with forces. There's some force pushing or pulling on this object to cause it to speed up or to slow down, or maybe even change direction. And so when we think about a velocity time graph, when we are looking at a velocity time graph, we want to make sure we know the axis, but now this point of reference, right over here, this 0, is not a point of reference anymore, but it means 0 velocity. So it tells us nothing about position. Now our origin here, our intercept on this axis, actually tells us our initial velocity. It doesn't really tell us our starting point. And where that ends up going to might tell us our final velocity, but it doesn't tell us anything about our ending point. So velocity time graphs don't tell you about position. They tell you about changes in velocity. And the fact that it's a line or a curve is going to tell you that if it's a line, it has an acceleration, and if it's a curve, it has a changing acceleration, whereas if it's a line, it has a constant acceleration. That is to say, if it's a line, it's experiencing a constant force acting on it, and if it's once that constant magnitude and direction, something is pushing and pulling on it with the same amount of oomph in the same direction. It's not changing. Or if it's a curve, that means there's a changing amount of oomph. The magnitude is changing, or maybe the direction that something is pushing or pulling is changing. And then how much it's sloping tells you how strong that acceleration is. Again, add numbers if you have to. So if you think about this, this is acceleration, which I'm going to go back one slide here. If these had been curves, you would have changing slopes. And because on a position time graph, velocity is the slope, a changing slope, like a curve would actually mean acceleration. So if you have a curve on a position time graph, that means acceleration. But if you have a line with slope on a velocity time graph, like this, you can see that here's something that started out moving with a negative velocity. So its initial velocity was to the left. It gets closer and closer to 0. So now is that 0 velocity? It means slowing down and stopping. And here it actually changes direction because up here it's moving in the positive direction. So this would be a graph of something that started out moving to the left, slowed down, stopped, and was now speeding up and moving to the right. This is a line, so it would be a constant force causing a constant acceleration here. It ends up starting out moving to the left and ending up moving to the right. This is a real kind of a trickier thing to understand than a position time graph, so I'm not going to ask you a lot about it. And then finally, there's acceleration time graphs. Pretty much if you see acceleration time graphs, they're going to be horizontal lines like this. So you can see the red line represents something that is moving with a constant positive acceleration. Maybe it's being accelerated constantly at 3 meters per second to the right. Remember that positive means to the right. Whereas this negative one is always to the left, or maybe it's down if it was y, or it would be backward if it was z. But in this case, This is experiencing a constant acceleration, which means it's experiencing a constant force. If it had been here, right on this axis, it would have been no acceleration, which would indicate a constant velocity. This is a little tricky, but you'll get it. Just keep plugging away.